Carboxylic acids turn up all over the place. The very smallest one is formic acid. It's a key constituent of insect venom and is really a bad actor when it comes to human tissue. You're much more familiar with its slightly bigger brother, acetic acid. Acetic acid is the sour component of vinegar, gives it its pungent smell. And it's not the only acid that tastes sour. In fact, the German word for acids is Säure, meaning sour, and sauerkraut is a German dish based on vinegar and cabbage. Butyric acid is also sour. It's a component in sour milk and smells even worse. It really is essence of dirty socks. A hamper full of dirty socks that have been kept there for a week or so is about what butyric acid smells like, so it's not real pleasant. And the dicarboxylic acid, malonic acid, is an important building block in biosynthesis of long-chain compounds, and it's also an important building block in the organic synthesis lab as well. By far the most extensive aromatic acid is benzoic acid, but we know it better as sodium benzoate. Sodium benzoate turns up in a lot of packaged foods because it's a preservative and provides much better shelf lives to foods in grocery stores. We eat a lot of it. Take a look at the labels in grocery stores sometime. The metabolism of sugar in muscle gives lactic acid, alpha-hydroxypropionic acid, and buildup of lactic acid is responsible for muscle soreness in overexercised muscles. Beyond that, let me show you a couple of others. This long-chain carboxylic acid is known as a fatty acid because it's derived from fats, broken down into long-chain carboxylic acids, which typically have double bonds in them. You see this one has 3 double bonds. All of them are cis, and one of them is 3 carbons from the end, which makes it an omega-3 carboxylic acid. We hear a lot about omega-3 fatty acids in relationship to nutrition. And look at this, a compound that looks a lot like this for a good reason. It's related metabolically. The skeleton of prostaglandins comes from long-chain carboxylic acids, where there's a single carbon-carbon bond to make a 5-membered ring. The actual prostaglandins have functional groups here and there: hydroxyl, ketone, alkene, and the location and identity of the functional groups determines their properties. So what I wanted to do was convince you that carboxylic acids are everywhere, that play important roles biologically and chemically, even in the kitchen. Let's take a look at some of their properties. The carboxylic acid functional group itself has 3 polar covalent bonds. The oxygen is more electronegative than carbon, so it pulls electron density away from carbon and toward the oxygen. And at the same time, it's more electronegative than hydrogen, so it pulls electron density away from the hydrogen as well. The net result is a partial negative charge on this oxygen, and on this oxygen, partial positive charge on carbon, and this hydrogen. Overall then, this functional group is highly polar. This affects its boiling point. The boiling points are elevated. This affects its solubilities. Typically, carboxylic acids are soluble in more polar solvents, and especially water. We'll talk about that in a minute. And it affects their chemistry. When you look carefully at this group, you see that it has an OH that could be involved in hydrogen bonding, and it has a second oxygen that could also be involved in hydrogen bonding. This leads to intermolecular interactions of 2 carboxylic acid molecules to form dimers. I've drawn 2 molecules of carboxylic acids here, each oriented in a direction that makes it clear that they could hydrogen bond. The OH from one molecule hydrogen bonding with a carbonyl of the other, while the H of that molecule hydrogen bonding with the other carbonyl. These guys form strong associations, and at the same time, they're very soluble in water because the same kind of hydrogen bonding can happen in water. Substituting water molecules for a carboxylic acid, you can see that there could be hydrogen bonding here with the carbonyl oxygen of the carboxylic acid, and here with the hydroxyl hydrogen of the carboxylic acid to a second molecule of water. So typically, carboxylic acids have elevated boiling points because of their dimerization, and they have elevated solubilities in water because of the hydrogen bonding with water molecules. This plays an important role in their chemistry. As you might guess, the most important chemical property of carboxylic acids is their acidity. When a carboxylic acid is put together with a base, and I'll show the base as having a negative charge, but it doesn't have to, it must have a pair of electrons, which can form a bond with that proton, leaving this pair of electrons on oxygen. In an equilibrium reaction, this carboxylate anion is formed rather readily because it's resonance stabilized. We can draw a second structure, which we picture as coming from having this pair of electrons shared between oxygen and carbon, as that pi electron is broken and a pair of electrons moving up on this oxygen. This resonance stabilization of the carboxylate anion is really important because it's what makes carboxylic acids really acidic. And I want to emphasize that this is an equilibrium reaction. That proton transfer can go in both directions, and which side is favored will depend on the strength of the base and the strength of the carboxylic acid itself. I'll talk about that another time. Carboxylic acids are strong enough acids that the proton is essentially quantitatively removed when treated with sodium hydroxide. Although in theory that's an equilibrium reaction, in practice this is essentially quantitative. The exact counter ion isn't important, but a cation that's typical would be sodium, potassium, ammonium, which I'm drawing in a different color because it's not really important. Carboxylic acids have typical pKa values of 4 to 5, and a pKa of water is about 15. Smaller values mean stronger acids, and stronger acids push toward weaker acids, so this equilibrium is shifted way to the right. So with typical bases, carboxylic acids are fully deprotonated. And one last thing about their acidity, carboxylic acids at a pH that's about 7 or 7 plus, physiological pH is maybe around 7.3, is almost completely deprotonated. So even under the slightly basic conditions of physiological pH, the carboxylate anion dominates. And that's why in biological chemistry, acetic acid is simply called acetate. Under biological conditions, it is acetate. Lactic acid would be lactate, benzoic acid, benzoate, and so on and so forth. My point is, under physiological conditions in plants and animals, carboxylic acids exist, but they exist as the conjugate bases, and they're referred to as the conjugate bases by name: acetate, lactate, benzoate, and so on. Now that I've told you how easy it is to make carboxylate salts, take a quick look at the behavior of these salts in water. You'll recall that carboxylic acids themselves have unusual water solubility because of hydrogen bonding. Well, that's even more so in carboxylate anions. Here's butyrate, the salt of butyric acid. And I showed the hydrogen bonding of the same type that we looked at before. This makes these carboxylate salts water soluble, even more so than the carboxylic acids themselves. But there's a limit. Take a look at this. When the chain attached to the carboxylate functional group becomes really long, this molecule becomes really conflicted. There's this water-soluble head attached to an alkyl group that's really long and water-insoluble. Molecules like this do a really interesting thing. There's a way that the heads can be involved with water and the tails get as far away from water as possible. Take a look. They arrange themselves in spheres. I've shown a circle here because I'm drawing in 2 dimensions, but these guys are spheres, and the tails are all sticking like toward the inside of a ball, with the water-soluble heads sticking out. So in water, long-chain carboxylate salts form clumps like this called micelles. They're water-soluble, but they have a water-insoluble inner side, and that inner side dissolves water-insoluble things. And this, folks, is the classic example of soap. Soaps are nothing more than long-chain fatty acids that form clumps, micelles, that dissolve dirt because it's water insoluble, in an inner core, but are carried away in the soluble form because of the outside carboxylate groups interacting with water all the way around the sphere. Without knowing it, our pioneers were doing interesting chemistry, forming micelles from fat to make soap. Today's soaps are pretty different. They have a lot of things added, and detergents, which are similar, have different water-soluble heads.